Euler's equations of rotation. Consider two different frames. The space frame, given by axis x, y, z, which is obviously inertial, and body frame, given by three unit vectors, E1, E2, and E3, which is rotating. In order to describe angular momentum in the form of tensor of inertia times angular velocity, we have to work in the body frame. Why is that? Because in the space frame, the orientation of the body will be continuously changing, which means that we can't use a constant inertia tensor. We would have to recalculate it all the time. So, therefore, it is for body frame that we can write a constant inertia tensor times angular velocity. More specifically, if we choose three unit vectors attached to the rotating body frame to be principal axis, then, as we know, the inertia tensor will be simply given by diagonal terms, where the diagonal terms are the principal moments of inertia. In which case, we write that L, angular momentum, as given in the body frame, will be given by lambda 1 times omega 1 for the first component, lambda 2 times omega 2 for the second component, and lambda 3 times omega 3 for the third component. On the other hand, in order to describe the equation of motion, we have to find derivative of the angular momentum with respect to a different frame, namely the space frame. Because then we can equate that derivative to the generalized force torque. So the question arises, how can we connect the derivative of angular momentum in space frame to the rotating body frame? Well, we already know the result, a general result, that space frame derivative of any vector, in our case it will be vector of angular momentum, is given by the body frame derivative. Typically we won't be carrying subscripts body when we describe vectors later, plus omega cross L. Again, L here is given in body frame. Now this is true for arbitrary vector, but we apply it for the case of angular momentum. So then we obtain the equation that gives us torque on one side and the derivative of angular momentum plus omega cross L in the body frame. These three equations, because we have three components, are known as Euler's equations. Now we know the first term on the right side is going to be simply lambda 1 omega 1 dot, lambda 2 omega 2 dot, and lambda 3 omega 3 dot, as given now always in the body frame. The second term, we have to compute the cross product, which in the body frame is given by the determinant, unit vectors E1, E2, E3, components of omega, omega 1, omega 2, omega 3, and components of the angular momentum, lambda 1 omega 1, lambda 2 omega 2, and lambda 3 omega 3, which gives us three components, E1 unit vector times lambda 3 minus lambda 2, omega 2 times omega 3, plus E2 lambda 1 minus lambda 3, omega 1 omega 3, plus E3 lambda 2 minus lambda 1, omega 1 omega 2. So combining all of this, we write the following three Euler equations that describe rotation. We'll have lambda 1 times omega 1 dot minus lambda 2 minus lambda 3 times omega 2 times omega 3 equal to the fourth component 1, gamma 1, then lambda 2 times omega 2 dot minus lambda 3 minus lambda 1 times omega 1 omega 3 equal to the torque component 2, and finally lambda 3 times omega 3 dot minus lambda 1 minus lambda 2 omega 1 times omega 2 equals to the torque component 3. These three equations determine the motion relative to the body frame. The torque is now given in the body frame, which is trickier than it seems because we have to keep track of the orientation of E1, E2, and E3, which is rotating with the body. And generally, this equation is hard to solve, with the exception for the case of no torque, in which case the right-hand side of all these equations becomes 0. So to describe a free rotation of a body, that's where Euler's equations are most useful.